everyone, welcome to our next week at STEMEY for physics. Today we're going to be talking about work and energy. So first up, we're going to be talking about the definition of both work and energy. The main thing to understand here is that work occurs when force is applied over a distance. And this connects to the first definition that you see, that energy is a measure of how much work one can accomplish. So work is the transfer of this energy, which is measured by force over a distance. And it can be a little bit confusing if you try to think of those things together because they seem pretty distinct. But the idea behind this is that as you apply a force onto an object, for example, if you push it, you are doing work on the object. And you can think about this in a sense that when you push something, you're causing it to move faster, which is kinetic energy. Of course, energy can come in different forms. It doesn't have to be kinetic energy, but this is often a concept that we try to understand and use that as an example. And we measure these in joules, which is kilograms times meters squared divided by seconds squared.
So as Tanvi mentioned, work occurs when you change an object's energy, and also that it's a measure of force times distance, but it's also equal to force times distance times cosine theta, where cosine theta takes only the component of force and the distance that are in the same direction. So what we mean by that is if you push a box and it's moving in the direction that you're pushing it, you're applying work. But let's say you're pushing the box straight down and it's moving horizontally, where you're not applying a force in the direction of motion, so you have no work. The units, of course, as you can see from this, are newtons times meters. Force is in newtons, displacement is in meters. Cosine theta has no units. And so the units are newtons times meters, which is kilograms times meters per second squared times meters, which is the joules that we just brought up. There's two forces that commonly cause work in AP Physics 1, which is the work due to gravity and the work due to friction. And so the work due to gravity is force times distance times cosine theta. And force in this case is the force of gravity, which is mg. Distance is just the height of the object, which is h. And cosine theta is cosine of 180 because gravity usually pushes down, and sometimes when the object's moving up, you have cosine of 180, they're in opposite directions. So the work is minus mgh. And in friction, we again have work as Fd cosine theta. The force is going to be mu times the normal force, and we have cosine theta again.
So now for the types of energy. We have 5 main types of energy, which include potential, kinetic, chemical, thermal, and nuclear. Potential is the energy that's due to a position. And the ones that we will cover are gravitational potential energy and spring potential energy. We also have kinetic, which is the energy due to motion, chemical, thermal, and nuclear. But in AP Physics 1, we really only focus on potential and kinetic energy.
So of the potential energies, as Tanvi mentioned, there's 2 types. The first is gravitational potential energy, and this is an object's energy, kind of the one you normally think about just in space, and that occurs because Earth has a gravitational field. And so the energy here is an object's mass times the acceleration due to gravity times height, which you'll notice is very similar to the work done by gravity, which we mentioned earlier. So you can see the units come back to joules as always. And what this tells us that if you have a more massive object, it has more potential energy. And if an object is higher up from the Earth, it has more potential energy. The other type of energy is spring potential energy. So let's say you have a block or some object attached to a spring, and then you compress or stretch the spring. Well, you know that the spring wants to go back to its original position, and so there's some energy that's stored up there. That energy is going to be equal to 1/2 times kx squared. And k, you'll remember from our unit on force, is the spring stiffness or spring constant of a spring. And x is, of course, the displacement. Again, the units come out to joules. And what this tells us is that if you have a stiffer spring, it'll give you more energy. And if you stretch the spring more, you'll have more energy. And you can stretch the spring in either way. So you can pull it, or you can you could pull it either way. You could compress it or extend it, but both ways provide the spring with energy.
And also one more thing to reiterate before I move on, K, as Keshav said, is just a constant, and that completely depends on the spring that you are working with. It's not necessarily something that you can search up like a gravitational constant. So a lot of times in AP Physics 1 problems, you're either given it in the problem or you try to determine it through some experimental procedures. But yeah, just to reiterate, it completely depends on the spring itself. And the second type of energy that we will be talking about is kinetic energy. And as we mentioned before, this type of energy is due to motion. And the formula of this is 1/2 mv squared. And the units, as we've been saying before, is joules. And you can see that once you look at the actual units of the variables of this equation, it does turn out to be joules again. And when we look at this equation, we can see the relationships between mass and velocity. So when you have a higher mass, you will have more kinetic energy. And when you have a higher speed or velocity, you'll also have more energy in that given object.
Now we're on to now that we've covered the different types of energies, we're gonna combine work and combine energy in the work energy theorem. And this basically states that work is the change in kinetic energy of a one object system. And as we have more objects, we'll talk a little bit more about this next unit in momentum and collisions. It can get a little more complicated, but we can see the derivation here actually comes from our third kinematic formula, which is the final velocity squared is equal to the initial velocity squared plus 2 times the object's acceleration times its distance. So if we rearrange for distance and we put that into the work equation, we can actually find that work is equal to 1/2 times the mass times the final velocity squared minus the initial velocity squared, which is the change in kinetic energy.
And now for this next topic, which is actually really important when you look at physics as a whole, is the conservation of energy. And the main principle in this is that when you're in a closed system, the sum of the potential and kinetic energy is conserved. And of course, there's a very specific scenario in real physics, which is a closed system. But when you think about AP physics and a lot of problems that you'll deal with in school, that basically means pretty much any situation. So what happens is that the idea behind this is if you look at the equation, you have that the potential initial energy plus kinetic energy and plus any additional work, which is applied to the system, will be equal to the total potential energy plus the total kinetic energy at the end of whatever event that you're looking at. This can be really helpful when you're trying to solve problems for an object's final height or an object's final velocity, because as we mentioned before, potential energy is equal to mgh, and kinetic energy is 1/2 mv squared. So that way you can work with those type of variables as well. And there's also the simulation that we wanted to mention before we move on, which deals with this really interesting way to play around, and you can create a skater park for this one person. And if you follow the instructions on here, you can see that you can build a graph where you can see how the total energy remains constant and the amount of kinetic and potential energy continue to vary depending on their height and their velocity. So definitely give that a look.
Now on to the practice problems. So our first practice problem is about finding the total energy in a system. So the first problem, we have a 5-kilogram bird that's 20 meters above the ground. Now we have 3 types of energy that we focused on. We have gravitational potential energy, which is based on an object's height. We have spring potential energy if an object is connected to a spring. We have kinetic energy if the object is in motion. Oh, it doesn't say anything about the bird in motion, and it certainly is not connected to a spring. The only energy we have to deal with is gravitational potential energy, which is equal to mgh. Mass is 5 kilograms. Acceleration due to gravity is 10 meters per second squared, which is actually the third term in this multiplication. And the height is 20 meters, and so we have 1,000 joules. The second problem, we have a 2-kilogram bowling ball, which rolls at 4 meters per second. For this, right, and I'll give a few seconds to pause the video in between each of these problems from now on. So for the second problem, we have a 2 kilogram bowling ball, which rolls at 4 meters per second. So I'll give you like 3 seconds to pause the video and then we'll come back. So hopefully you realize that when the ball is rolling, it doesn't have any gravitational potential energy because it's on the ground. It's also not connected to a spring. The only energy it has is kinetic energy, which is equal to 1/2 mv squared. Its mass is 2 kilograms. Its velocity is 4 meters per second. So its kinetic energy is 16 joules. For part C, we have the same 5 kilogram bird, which is 20 meters above the ground, but now it flies at 1 meters per second. So again, I'll give about 3 seconds to pause. And hopefully you found that this bird actually has both gravitational potential energy and kinetic energy. It has kinetic energy now because it's flying at 1 meter per second, so it's moving. And its gravitational potential energy, which we found earlier, was 1,000 joules. Its kinetic energy is simply 1/2 mv squared, where m is 5 kilograms and v is 1 meters per second. And so we have a total of 1,002.5 joules. And for the last problem, we have a spring with stiffness 4 newtons per meter attached to a 6 kilogram block. And the spring is now compressed 12 meters from its equilibrium position. So find the total energy. And for this problem, we don't know anything about its height, so we can assume it has no gravitational potential energy. We also know that the block is not moving, so it has no kinetic energy. For the spring potential energy, we do know that it's equal to 1/2 kx squared, which is 1/2 times 4 newtons per meter times 12 meters squared, which is 288 joules. It's important to notice here that the mass actually did not matter for spring potential energy. We could have had a 12 kilogram block or a 50 kilogram block, but whatever it is, the spring potential energy will be 288 joules.
Okay, so now for our next problem. And here we're going to try to find the algebraic energy, which is basically going to be using variables instead of actual values. So first up, Arthur is on the 3rd floor of an apartment. If he is X meters above the ground and has Y energy, how much energy will he have on the 9th floor? And keep in mind is that the 9th floor is 3x meters above the ground. So I'll give you again 3 seconds, pause the video and give it a shot. So for this problem, first we're going to try to find how much Y actually equals. So we know that because we're dealing with height and there is no velocity and there is no spring involved, the only energy that we have to deal with is the gravitational potential energy. So therefore, we know that mgh, which we will, instead of h, we'll use x because that is the number of meters that we are given, is equal to y. And when we try to find the final gravitational potential energy, instead of putting x, we're going to put 3x because now we know that he is 3 times higher than he was before. So we get that it equals 3 times mgx if you just rearrange where the 3 is located, which when you compare it to the initial gravitational potential energy is 3 times that amount. So we know that it is 3y. And keeping that in mind, we're going to try a very similar problem. A string is attached to a block and is compressed x meters. The block is released and travels at v velocity. What is the block's velocity when the spring is compressed 3x meters? So again, give you 3 seconds, pause the video and give that a shot. So now we're going to be doing a very similar process with this, but it's a little bit more complex. So we know that when we have a spring is attached, we have it compressed x meters, and when it's released, it travels at v velocity. And the idea behind this is that when the spring is compressed, it has a certain amount of energy. And then when the block begins moving at its highest velocity, which is at v, all of that spring energy is in the sense of kinetic energy at this point. And therefore, when we look at this equation, we can set the spring energy equal to the kinetic energy. So when we look at this, we can see that because x and v are proportional, because we can say because x squared and v squared, and therefore x divided by v should be some sort of constant, which we're just going to label as n for now. And therefore, we know that x times n, some value, times v should equal x. So if x changes, v must also change. And therefore, we can set up this ratio. if 3x divided by some value that we're trying to derive should also equal n, and x divided by v should also equal that n value. So therefore, we know that the question mark, which we're just going to have some variable, is equal to 3v, because 3x divided by 3v is also x divided by v. So it's just putting some sort of ratio, which is another tactic in trying to solve these problems.
So now that we've gotten the hang of energy with actual numbers and energy with algebra, we're going to turn to work. So for the first problem, we have John pushing with a constant 30 Newton force on an 8 kilogram box, and it moves 6 meters, and we want to find the total work. So I'll give you 3 seconds to pause, and then we'll come back. So as usual, we use the formula work equals force times displacement times cosine theta. We know that the force is 30 newtons. It moves 6 meters. And since he's pushing along with the direction that it moves, the angle between is 0 degrees. So 30 times 6 times cosine 0 is 180 joules. It's also important to notice that the 8 kilogram box was once again irrelevant here. So oftentimes you'll find that in energy and work and even kinematics, mass is not useful for the problem, but the AP will try to trip you up with that. For part B, we have John pulling the 8 kilogram box at an angle of 60 degrees. So you can imagine he has a rope and he's pulling it up at an angle. Again, he uses 30 Newton force and it moves 6 meters again, but we want to find the work he applies this time. So work is equal to force times displacement times cosine theta. The only thing that changes this time is that cosine theta becomes cosine 60 since he's pulling at an angle of 60 degrees. So if we do the calculations, you should get 90 joules. And for the final problem, we have an 8 kilogram box that's sliding past John, and then John pushes straight down, and the box still moves 6 meters. So once again, we're going to try to find the total work. So as usual, we can use work is equal to force times distance times cosine theta, except this time, since John is pushing straight down and the box moves straight forward, there's an angle of 90 degrees in between them. And since cosine of 90 is 0, John actually applies no work on the box. So you can see how important the angle theta is in determining the work applied on an object.
And also, just on that point that Keshav was talking about, when we think of doing work on an object, you can also think of it as putting energy in the system, which is like if you push a box up, you're putting energy into it and giving it gravitational potential energy. But a common thing to think about when you're doing this is that if you move the box in like a curved manner, even though you are feeling like you're putting more work into the system because it's taking more of your body energy, physically you're actually doing the same work as you would do if you just push it up straight. And that comes to what Keshav was talking about, that the energy has to be in the same direction, the force has to be in the same direction as the distance. So therefore, because John is pushing straight down, he's actually doing no work on the system, even though I'm sure John physically feels like he is pushing the block. So now we're going to do some problems related to conservation of energy. So first up, a 10 kilogram egg is at rest at 20 meters above the ground. It falls. What is the speed just before hitting the ground? So again, just around 3 seconds, pause the video and try out the problem. So the main idea behind this is that you have to realize that because the egg is at rest when it's 20 meters above the ground, by the time it reaches the ground, all of that gravitational potential energy is converted into kinetic energy. And therefore, we can set mgh equal to 1/2 mv squared. And then we can solve for v because we're trying to find out the velocity that that the egg is at. And then we can plug in the values for g, which is 10 approximately, the height, which is 20 meters, and then we get that will be at 20 meters per second just before it hits the ground. And again, you might think that you're going to need mass in this because both formulas actually use mass. But you actually don't need mass because they cancel out. So it's actually really helpful to remember the formula that velocity equals the square root of 2gh when all of the gravitational potential energy is converted into the kinetic energy. So now the next problem. Arthur throws a 6-kilogram ball straight up at 3 meters per second. How high will it go? So for this, it's really just the exact same problem that we did before, but you flip it. So we have how much kinetic energy the ball will have, but we want to find its maximum height. And therefore, we can set them equal to each other, cancel out the masses, and solve for the height, and we get 0.45 meters. And again, just before we go on, I just want to reiterate, there are really a lot of key things to take out from here. Another one is that you might think that you're going to need to use some sort of kinematic formula for these problems because you see the mass and you see a velocity and you're trying to figure out how high it's going to go and you want to find the components of the velocity. But you don't actually need to do that because it's a lot easier to just set these variables equal to each other and plug in the values that you already know. And it's almost just literally a one-step problem. But if you want to use kinematics, you have to find the component of velocity, plug it in, find the time, and then plug it into another formula and get the height. So it's really an important trick to remember. And our last problem. A 20-kilogram roller coaster moves at 30 meters per second at point A, which is this image right here. How fast will it be moving at points B and C? So give that another shot and we'll get back. So when we look at these problems, it's conceptually very similar to what we've been using and the ideas that we've been thinking about before. So first up, we're going to solve for how much energy it had at the very top. So we have its velocity, so that's 30 meters per second, and we also have its height, which is 200 meters. And that equals 40,600 joules. At point B, which is at the very bottom, we only have kinetic energy because gravitational energy, it depends on the height. And we're assuming that the height at point B, because it's at the ground, is 0 meters. So we know that all the energy is kinetic, and we can solve for V, and just using that value from before, we have 63.71 meters per second. At point C, we have a very similar idea with the conservation of energy, but this time, not all of the energy is in just the kinetic energy. In fact, we have some of it because of this height at 160 meters. We have some of that energy as the gravitational potential energy. So therefore, that we have 1/2 mv squared plus mgh must equal that total energy that we saw for up here. And therefore, but we have the mass, we have the height, and we have gravity. So we can still solve for V with relative comfort. We just need to use these values, rearrange it for V, plug it in, and we have the answer right here. Now 29.32 meters per second.
For the next problem, we're going to be using the work energy theorem. For the last one, we mostly use the conservation of energy. So we have a 6-kilogram block, initially moving at 8 meters per second on a rough surface. It travels 4 meters before coming to rest. What is the work done by friction? So I'll give you 3 seconds to pause. And let's continue. So because it's a rough surface, we do know that there's work done by friction. And the work, as we mentioned, this work is equal to the change in kinetic energy. So the change in kinetic energy, at the end, its final velocity is 0 meters per second because it comes to rest. At the beginning, it's 8 meters per second. And we know its mass is 6 kilograms. And so kinetic energy is 1/2 mv squared. The final velocity is 1/2 times 6 times 0 squared. The initial velocity is 1/2 times 6 times 8 squared. And so the work done by friction is actually negative 192 joules. Again, it's negative because the block moves forward. The block moves forward, but friction applies a force in the other direction. So cosine is equal to 180 degrees, which is -1. For part B, we have the block now traveling at 10 meters per second on a rough surface. And this time we're given that the kinetic coefficient of friction is 0.3. And again, we want to find how far will it travel. So for this problem, we again use the work energy theorem, but we also use the definition of work. So we know that the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. The final kinetic energy is 0 because it comes to rest and velocity is 0. The initial kinetic energy is 1/2 times m times v squared. Now actually we don't know what the mass is, but we know that the initial velocity is 10 meters per second. And so we know that the work will be equal to minus 50 times the mass of the block. We also know that work is equal to force times displacement times cosine theta. The force done by friction is mu mg, which is mu times the normal force. And so if we plug in the numbers, we get that the work is equal to 0.3, which is mu, times 10, which is g, cosine 180, which is cosine theta, times m times d. And we want to find d. Now we can set the two works equal to each other. We know that minus 50 times m is work. We also know that 0.3 times 10 times cosine 180 times m times d is equal to work. And so if we set them to each other, we get that minus 50 is equal to minus 3 times d, and d is equal to 16.67 meters.
And now we have some challenge problems at the end, and these will be combining the ideas of work and energy that we've been working on before. So we have a 2-kilogram block is suspended 6 meters above the ground and attached to a horizontal spring with stiffness of 10 newtons per meter. The spring is then extended 70 centimeters and the block is released. What is the magnitude of its final velocity just before it touches the ground? So again, 3 seconds, pause the video, try this out. Maybe try drawing a diagram because that always helps. So for this, what the really key concept and idea behind this is understanding that the energy is actually distributed in 2 different components. We have the horizontal and we have the vertical. In the horizontal, we have our spring energy, which is k, 1/2 k, the constant, times x squared, and that is all converted into velocity, which is 1/2 mv squared for kinetic energy. And we can solve that in our horizontal component. We have the velocity is equal to the square root of kx squared divided by m. In the vertical component, we actually don't have the spring energy, but instead we have our gravitational potential energy. But conceptually, it is the same, that all of this energy is being converted into kinetic energy. So we have that same formula that we used before. V is equal to the square root of 2gh. And as we learned in our projectile motion slideshows, when we're talking about the total magnitude of the final velocity, we have to actually use Pythagorean theorem to use the horizontal and the vertical components, so that we get the square root of horizontal squared plus vertical squared. But we're just going to put in the formulas that we had before, and we solve, and we get that the total velocity is the square root of kx squared divided by m plus 2gh. And using that formula, we can solve and use the values that we had before. And again, what's important to recognize here, and don't get stuck, is that we have 70 centimeters, not 70 meters. And the formulas here work with meters. So you have to make sure that the values that are using are actually indeed the ones that do work for the formula. So therefore, instead of 70 here, we have 0.7, so that we're using the meter value. And we get that the total velocity is approximately 11.27 meters per second.
The last problem, we have a 1-kilogram block. It's compressed 30 centimeters on a 7 newton per meter spring. Then it is released on a rough surface with kinetic coefficient of friction equal to 0.1, and we want to find how far it slides. I'll give you again 30 seconds to pause and try it out on your own. If you could do this problem, you're pretty good to go. But first we need to know that conceptually speaking, first the block will take its spring potential energy and convert that to kinetic energy, and then the work done by friction will slow it down until it has no energy left. So we can set that all together with first, spring potential energy is 1/2 kx squared, setting that to the kinetic energy is 1/2 mv squared, and we can find that the velocity will be square root of kx squared over m, and that's actually 0.79 meters per second. So as soon as you release the block, it will be moving at 0.79 meters per second. Then the work will be equal to the change in kinetic energy. Now we know the final kinetic energy is always, not always, but it's again 0 joules, because the final velocity is 0 meters per second because it comes to rest. And we know the initial kinetic energy because we know the block's mass, and we now know its velocity is 0.79 meters per second. So you know the work done by friction is minus 0.31 joules. And the final step is to set the work energy theorem to the definition of work, which is FD cosine theta. And because friction has F equal to mu mg, we now know that minus 0.31 joules is equal to mu, which is 0.1, times m, which is 1 kilogram, times d, which we need to find, times the acceleration due to gravity, which is approximately 10 meters per second squared, times cosine theta. And here, again, with friction, theta is usually 180 degrees because the block moves one way, friction acts the opposite way. And so we can set that all together and we find that the distance or the displacement will be 0.31 meters.
So that is all from us today. Hope you enjoyed our video. Make sure to join us next time. You can join our Google Classroom, which is in the comments below. And make sure to give us some feedback. Thank you.